Hello friends, good afternoon and welcome to EduSite Live Lectures. Dear friends, as you know that we started a series on quantum chemistry and today we are conducting yet another lecture in the same series. In today's lecture, we will be continuing with the concept of operators. To discuss this topic, we have with us our subject expert Dr. Amita Dua. Dr. Dua is Assistant Professor in Department of Chemistry in Dayal Singh College, University of Delhi. Without further ado, I would like to welcome ma'am to our studios and request her to start the lecture. Welcome ma'am.
Thank you. So hello to everyone. In the last lecture we have started with the topic operators, and today I'll continue with the same topic, that is operators. So in the last lecture we have discussed about what is an operator. Actually, operator is a command which converts one function into the another function, and we have also discussed about the algebra of operators. I have discussed about the addition, how if the two operators are given, how they are, both of them are added, how they are subtracted, how do we multiply both the operators. And today we will discuss about the commutative property of the operators, that what do you understand by the commutation of the two operators. So you can see on the slides, by the slides you can see all the expressions. So what do you understand by the commutative property? Commutative property is, suppose we have two operators, A operator as well as B operator. Now if we want to see whether they commute with one another, we have to multiply both the operators. And always to perform the algebra, we need one function, because it is just a command. A command, like it is just a doctor. For a doctor to work upon, you always need some patient. So who is the patient? That is the function. We always need one function on which the operators operate, whether we do addition or subtraction or multiplication or commutation property. We always need one function, that is, and if function is not given, we always take an arbitrary function, let it be fx. So suppose we have two operators, A operator as well as B operator, and we have to see whether these two operators they commute with one another or not. So in this case, we always multiply the two operators. Suppose you can see on the slide, we have two operators, A operator and B operator. So first we multiply A operator into B operator and subtract from the reversal order, that is B operator as well as A operator. So if the two operators are such that the result of their successive applications is the same, irrespective of the order of operation, that is, if we multiply A with B or B with A, if the answer comes out to be same and we subtract the two, then the difference comes out to be 0, then the two operators are said to commute with one another. Just see the slide. You can see the expression for the commutator, that it is simply, you must have read the dot product as well as the cross product. So for the commutation property, we take the dot product. Suppose we have two operators A and B, we just take the dot product, that is A dot B. What would be A dot B? That is AB fx, A into B into fx minus B into A into fx. So if this difference is known as commutator, if the value of commutator comes out to be 0, then we said that A and B they commute with one another. So we can discuss one example over here, like suppose we have one operator, A operator, let it be d by dx. Just see the slide for the example, and the B operator is del square by del x square, and suppose the function is sin x. So first we'll do it in steps. Suppose first we will take A, B, fx. So what is A operator? That is d by dx. What is B operator? D square by dx square. And what is fx? That is sin x. I have already told you that whenever the multiplication part is done, we have to go from right hand side to left hand side. So what is the double differential of sin x? Sin x will first convert it into cos x and then cos x into minus of sin x. So the answer of that bracket would be minus sin x. Again, when the differentiation is done, sin x will get converted into cos x and minus sign would remain as such. Now we will take the reversal, the reverse multiplication, that is b into a fx. Now what is B operator? D square by dx square. What is A operator? D by dx. And what is fx? That is sin x. Again first apply the B operator upon the function fx. So d by dx of sin x will become cos x, and again the double differential of that cos x will again give the answer minus cos x. Now we will calculate the commutator. What is commutator? It is the difference of the two multiplication, that is ABfx minus BFX. Now on subtracting minus cos x from minus cos x, the answer will comes out to be 0, and this shows that the two operators A and B are commute with each other. So the main thing is that what is commutator, and whether how do we calculate the commutator part, and whether after calculating the commutator we have to see, it will tell you whether these two operators they commute with one another or not. If the commutator, the value of commutator comes out to be 0, it means that two operators they commute with one another. Similarly, on the other hand, it may happen that two operators do not commute with one another, and this happens when the value of the commutator it comes out to be non-zero, that there is some value, it is not 0, but some different value is there. You can see one example just to understand this thing. Suppose we have an operator A, let it be x, and B operator is d by dx, and the function is x square. Again in the first step we will calculate ABfx. What is A? You can see A operator is x, B operator is d by dx, and fx is sin x. Sorry, fx is, the function is x square. So first d by dx of x square is 2x, and one operator is already standing outside the bracket. This is just multiplied because x alone cannot do anything. It is just multiplied by 2x, so it will become 2x square. Similarly, BAfx, again by putting all the values, that is B operator is d by dx, A operator is x, and the function is x square. First we always start from right hand side, x is multiplied by x square, it will become x cube, and then d by dx would become 3x square. This is a simple differentiation which we have done. And on subtracting the two, we get the answer minus of x square, which is a non-zero value, and this shows that A and B they do not commute with one another, and thus in this case A operator and B operator are non-commutative to each other. Now the thing is why we are, this we'll discuss later, that why we are doing operator part, what is the help do we get by these operators in quantum mechanics. That is a later on part. After the operators we will discuss all these things in quantum mechanics. But the first thing is, what is the significance? What does this commutation means? Commutation means because every operator has its physical significance in quantum mechanics. Later on during this, still we are just taking simple operators like A operator or B operator, but in quantum mechanics instead of this we will take momentum operator or kinetic energy operator or energy operator or time operator, position operator. So those kind of things are given in quantum mechanics. So you should know that what do you understand by, suppose I am saying that yes, A and B they commute with one another. What does this mean? This means that at the same time, if they commute with one another, means that the value of A, because every operator has its physical significance, it means something in quantum mechanics. So A and B commute with one another means we can calculate the value of A as well as B property, because in quantum mechanics it indicates some property. Operator means some property in quantum mechanics. We can calculate the value of the two properties at the same time. Like suppose in quantum mechanics I take position and momentum, and I have to check whether I can calculate the two values, the value of position and momentum at the same time. So if they commute with each other, this means that yes, we can calculate the value of position and momentum at the same time. So this is how it will help you. The operators would help you in quantum mechanics to decide whether you can calculate the two properties at the same time or not. So if the two operators, so what is the physical significance of commutation is that if the two operators commute, that is the dot product comes out to be 0, then the two properties, the observable properties, I am already telling you that the observable properties, why? Because operator later on operators are the properties. In quantum mechanics we never ever have any equation to calculate the momentum, it is a momentum operator which will help to calculate the momentum from the wave function. So the two observable properties are represented by, and this that can be simultaneously and exactly determined. However, if they do not commute, the answer does not comes out to be 0, it means that the two values cannot be calculated at the same time. Now to discuss, to understand more, I am doing some problems on the basis of commutators. Like suppose we have question number 1, you can see on the slide, that show that the two operators, they commute with, I have already done the multiplication, the addition and the subtraction part in the last lecture, and today you can see that I am doing the problems on commutation part, that show that the two operators, they commute with each other. Suppose we have the first part, you can see, suppose we have one operator d by dx and the b operator is 3 plus, and if the function is not given, I am telling you again and again, if none of the function is given, you can take an arbitrary function, let it be fx, which I have taken in this example. So will obviously to calculate whether they operate with each other or they commute with each other or not, we have to calculate the commutator part. Now what is commutator? That is a dot b. And how will you calculate the dot product? That simply ab minus ba, and on what it is operated, that is the function fx. So it will become, first we will calculate the AB, that is a dot b, and then we will calculate ba. So you can see that is AB. What is A operator? A operator is d by dx, and what is B operator? That is 3 plus. And then we have to write fx, because we always start operating from right hand side. So 3 plus fx, it is simply, it will become a function, and we will operate d by dx upon 3 upon fx. So what would be the answer? When d by dx is operated on 3, it is a constant, answer will comes out to be 0, and once it is operated on fx, the answer will become df by dx. Again, now we will do the second step, that is b operator, a operator, fx. What is b operator? Simply we can see from the numerical, it is b plus, and then what is a operator? D by dx, and they both are applied on the function fx. Again starting from the right hand side, d by dx of fx will become df by dx, and this is 3 plus df by df, by dx. Now calculating the commutator, that is a dot b, this would be ab minus ba, and on cancellation the answer comes out to be minus 3, and this shows that because it is minus 3 is a non-zero value, and this shows that because the commutator is not 0, and thus a and b, they do not commute with one another. Similarly, you can see the second part of this numerical. Suppose the operator are a operator is 3 plus and b operator is 4 plus and fx is ax. So first again the same steps would be there. First we will calculate abfx, answer is 7 plus ax, and then we will calculate ba. Ba would be 7 plus ax. On subtracting the two, answer comes out to be 0. This shows that the a and b, they commute with one another. Second question, calculate the evaluate, they are asking you to calculate the commutator, that is a dot b, if a operator is d by dx, b operator is 3x square, and the function fx is given as sin x. So we will calculate a dot b, the procedure will remain the same. I am not, in this question I have not taken all these steps, I am doing it in one step only. You can see ab, what is your a operator is d by dx, b operator is 3x square and sin x, and then subtracting from b operator, that is 3x square, a operator is d by dx upon sin x. So one should always know that how do we differentiate the multiplication part, that whenever there are two functions a and b and we have to do the differentiation part, then it is always taken as first function into the d by dx of second function plus second function into the d by dx of first function. The simple differential formula, the simple differential algebra I have applied on this So now we have to do the d by dx of 3x square into sin x. So it will become sin x will remain sin x, the differentiation of 3x square would be 6x plus the first function 3x square, and d by dx of sin x will become cos x, minus the second part you can see 3x square, d by dx of sin x is cos x, so answer is 3x square cos x. So on subtracting the common part, it will get cancelled, so we land up to 6x into sin x, because again it is a non-zero value, the commutator, the two operators, they commute with one another. So by this you can see many problems. I am doing this just to clarify that what is commutation, and even the mathematical one should also know how to do the calculation part. That is why I am discussing all these problems with you. Like you can see question number 3, calculate the commutator, that is a dot product, if A operator is d square by dx square and B operator is x, because you can see that none of the function is given. So I am simply taking the function as fx. So we can calculate the dot product, that is AB, that is AB minus BA fx, put all the values, my A operator is d square by dx square, my B operator is x. By seeing the screen you can see that how to put the values. One should always know which one is to be multiplied first. This is the only thing why I am showing all these questions, just to clarify all these things, how one should multiply. So your A operator is d square by dx square, your B operator is x, and then fx. Always start solving from right hand side, subtracting, the B operator is x, your A operator is d square by dx square, and again the function, that is fx. So whenever the double differential is there, one should always differentiate one by one. So if you have to differentiate twice, first that is twice the differentiation is to be done. So suppose we have d square by dx square of what? Of x into fx. So first x into fx, first of all it is differentiated, and again whatever the answer comes it is differentiated again and again. So once it is differentiated, suppose we have d by dx of x into fx. So first it will become what? It is first function, that is x, into d by dx of second function, that is df by dx. Again the second function, that is fx, into d by dx of x, which comes out to be 1. So that bracket will become x df by dx plus fx. Because it is a double differential, so again we will differentiate on this bracket. So this will become, that is x into the double differential del square f upon del x square, plus again the differentiation, that is df by dx into d by dx of x, that is it will become 1. So this is how the bracket is solved, and cancelling the common things, so we land up to twice of df by dx. Again because the value is non-zero, therefore the two operators, that is A operator and B operator, they do not commute with one another. So there are many problems you can see, I have given just to solve them, and by solving them the things become more clarified. Now you can see question number 5, I am showing you on the slide. Like find whether the two operators, A operator is d by dx and B operator is x, they commute with each other or not. The same thing, the same procedure is repeated, like A operator is d by dx and B operator is x, and the function is fx minus x into d by dx upon fx. The simple differentiation is to be done on x upon fx, which is x into d by df by dx plus fx minus x into df by dx. The two things gets cancelled and we are left with fx, and this shows that they do not commute with one another. Why? Because there is a thing which is left. Now the question number 6 is very important, and the concept of this question will be used later on in quantum mechanics. By this you can also show how the Heisenberg principle comes into the picture. Like suppose we have, because I always told you that operator up till now we are taking operators just as simple like A operator and B operator. But actually in quantum mechanics, operator are the observable properties. Like they are asking you that find the commutator. What is Px? This is the topic which we will take after the operator, that the Px operator or the momentum the Px is the momentum operator. They are asking you that there are two operators, Px and x square, whether they commute with one another or not. So what is Px? That is the momentum, and what is x? X square is the distance. So how will you calculate the dot product? We are simply taking the dot product, that is Px into x square, like we are taking AB into Fx minus BA into Fx. Here instead of A operator we have Px operator, instead of B operator we have x square operator. So we are taking AB minus BA into Fx. Now what is Px operator? Minus I h cross d by dx. No need to worry that from where all these operator have come, the expression of P operator. This we will do after this topic, that where we have got this Px operator. So suppose this expression is given to you, suppose you have Px is minus I h cross d by dx. And what is h cross? One should always know what is h cross. H cross is h upon 2 pi. I have taken the compact form, I haven't taken h upon 2 pi just to simplify the calculation. I am simply taking h cross. So what is h cross? Is h upon 2 pi. Now Px is minus I h cross d by dx. And what is x square? It is simply x square. And then minus of x square, because we are taking b into a. Now what is b? B is x square, and what is Px? Minus of I h cross d by dx. And obviously we have to take some function that on which the operators are operating, so we are taking Fx. So now simply solving this thing, that taking Fx into the brackets, it will become minus I h cross d by dx x square into Fx, and minus minus will become plus I h cross x square multiplying the Fx, because I am taking the Fx inside the bracket, so it will become df by dx. Because it is a differentiation and I h cross is just a constant, I is iota, the imaginary number, so it is minus I h cross. So on differentiation, because again applying the multiplication formula of differentiation, that is first function into the d by dx of second, that one. So by this we will solve the problem, the bracket part, that is x square into df by dx plus Fx into d by dx of x square, that is 2x. And the next expression will remain as such, because nothing is to be operated, it is a simple multiplication part. So the two things gets cancelled, minus h cross is multiplied with the bracket and the two expression would get cancelled, and the answer comes out to be minus 2x h cross Fx. This problem shows that momentum and the position, the square of the position, do not commute with one another. Do not commutate means that we cannot calculate the value of the momentum and the square of the position at the same time. This helps in quantum mechanics, and this was actually it was also stated in Heisenberg principle that the position and the momentum, we cannot calculate the position and the momentum of a moving object with accuracy and simultaneously at the same time. And this also shows that. Like the similar problem, because in problem number 5 or 6 I have taken momentum operator and x square, the square of the position, whereas in question number 8 I have taken the exact problem that calculate the commutator, that is momentum operator and position operator, whether they commute with each other or not. The answer is exactly same as we have done question number 6. In question number 6 I have taken x square, whereas in question number 8 I am taking the position part, that is x. So you have seen that on solving the procedure will remain the same. The only thing is that instead of x square, here the calculations are more simpler, because there it was x square, here it is x, and answer comes out to be minus I h cross Fx. And this shows that we cannot calculate the position and the momentum of a moving object at the same time, and this is in accordance with the Heisenberg uncertainty principle, what Heisenberg said in his statement. you can also see one more problem. Show that if two operators A operator and B operator, suppose there are two operators A and B, they commute with one another, then they have also same set of eigenfunction. Eigenfunctions, what were that is a well behaved function. The eigenfunction will also discuss after this topic, that what are eigenfunction. Suppose we have an wave function that is psi a, because obviously if two operators are given, operator will always operate on some wave function. Without wave function we cannot do anything. So suppose we have a function that is psi a, and it operate, and suppose an operator A is there which operate upon the wave function that is psi a, and the value comes out to be, that is when the operator A operator, it operates on the function that is psi a, the answer comes out to be, that is A and the wave function. So what is an eigenfunction? Before doing this problem you should know that what is an eigenfunction. So eigenfunction is one that whenever there is an operator and it operates on some function and the function comes out to be same as it is. Suppose we have psi a, and on operating that operator on psi a, the answer comes out to be psi a with some value multiplied, with a constant multiplied, then that wave function is said to be the eigen wave function. I am repeating once again that what is an eigenfunction? Eigenfunction is the one if in any case some operator is operated on that wave function, the wave function comes out to be as it is with a function with a constant multiplied, then it is known as eigenfunction, and the value multiplied is known as eigenvalue. You can see the first expression of this numerical. Suppose we have an operator A operator and it is operating on psi a, that is a function, that is a wave function, and on solving, on operating, the answer comes out to be some constant multiplied by that wave function, then wave function is an eigenfunction, because they are asking, they are the numerical is like that. So I can write this expression because I assume that let there is an operator A which is operating on the wave function that is psi a, and the eigenvalue A is the eigenvalue, and the wave function comes out to be as it is. Now they have also given that A and B, they commute with one another. What do you understand by commutation? That is the multiplication of the reversal is also same, that is AB equals to BA. Now in this expression AB BA, I will multiply psi a on both the sides. Now what will this become? AB psi a equals to B operator A operator into psi a. Now I am taking B operator and psi a in brackets, and similarly on the right hand side I am taking A operator and psi a into brackets. You can see on the slide everything, you can see on the slide. Now in the right hand side, the thing I am taking, that is A operator into psi a, you can see in equation number 1. What is A operator into psi a? That is small a into psi a. I will put this expression, that is I have written using 1. So this will become B operator into small a into psi a. Is it? So what does this mean? Now I am rearranging this equation. I will take that small a out of the bracket and take B operator inside the bracket. So this will become, that is small a B operator into psi a. So because on both the sides you can see that, what do you understand by this equation? Because I have already told you that what do you understand by the eigenfunction. Eigenfunction is that whenever an operator is operated on some function and the function comes out as it is with a constant multiplied, and this what you can see in the last expression, that when A operator is applied on B operator upon psi a, the answer is coming out to be small a and again B operator into psi a. Because so my wave function is B operator into psi a, because B operator into psi a is coming as it is with a constant multiplied, and therefore B operator is also an eigenfunction of the A operator with the eigenvalue A. So like this, A operator and B operator, they have same set of eigenvalues. So by this we can do the similar numericals. You can see like one more numerical you can see. Determine whether the operator A operator is given d by dx and B operator is d square dx square plus twice of d by dx, whether they commute with one another or not. So as simple as that, I am taking the two operators A and B and I will take the dot product, that is first I will calculate AB into Fx and then I will calculate BA into Fx and simply subtract the two. So what is my A? So A is d by dx, what is B? D square by dx square plus 2 into d by dx. We simply have to write the expression. A and B is always given you in the question. If Fx is given, put it instead of Fx, and if Fx is not given, you simply have to write Fx to solve the questions of numericals of operator. So just by putting the values of A and B and then B into A, now what is my B? D square by dx square plus twice d by dx, and what is my A? D by dx. And at the end I have taken a function that is Fx. Now simply solving the brackets one by one, I have taken the d by dx. What would be d by dx of that bracket d square by dx square? That would become d cube by dx cube. And then d by dx of 2 into d square by dx square. D by dx is simply multiplied because 2 is a constant. So d by dx will become d square by dx square. And then again solving the next bracket. So by this and then entering Fx. So finally we have seen that all the expressions are getting cancelled, and once they are cancelled the answer comes out to be 0, and this shows that the operators A operator and B operator, they commute with one another. So by this the commutator property we have discussed about the algebra. Up till now I have told you that what are operator and what is the algebra of operators. I have shown you how to subtract the two operators, how to add the two operators, how to do the repeated multiplication or the simple multiplication of two operators, and even the commutation property with all the numericals. And now I will discuss about, because actually we will discuss the operator topic in quantum mechanics. So you should know what kind of operators, because we never deal with A operator or B operator. These are the general operators, general symbols which we are using, because I have to make you understand what actually what our operators is. But what kind of operators do we deal in quantum mechanics? So because in quantum mechanics we have different kind of properties are there, like kinetic energy, like momentum, like position, like potential energy, and all those things are related, and for every property we need operator, and this we will discuss once the operator topic is finished. We will discuss that what is the need of operator in quantum mechanics. Before starting the postulates of quantum mechanics, the main important thing is what is the requirement of operators in quantum mechanics, and before that we should know that you should know what kind of operators do we deal in quantum mechanics. So now I will start with that is the kind of operators which we will use in quantum mechanics. So first, the most important is that is a Laplacian operator. What is Laplacian operator? It is a simple differential operator which is used in quantum mechanics. This you can see, it can be shown by a sign delta. It is I cap d by dx, j cap, this you have to learn, the expression has to be learned. There are 5 and 6 expressions in totality which are used in quantum mechanics, and these are given. I am explaining you how these comes, what are the derivation of all these operators. So it is very important differential operator which is used in quantum mechanics. So first one is del, that is I cap d by dx, j cap d by dy, and k cap d by dx. I am simply taking the dot product, that is del square. So this del square would be, because I dot I is 1, j dot j is again 1, and k dot k is 1. So we simply land up with del square by del x square, del square by del y square, and del square by del z square. The addition of these, that is what is del square? because we always deal with del square. More than del, we deal more with del square. So, it is d square by dx square, the partial differential, del square by del y square and del square by del square. This is the first operator which we are going to use in quantum mechanics later on. You can see the slide next, that is the momentum operator, the most important operator which we will use later on. I am showing you the derivation. Ultimately, you should know what is the final expression. One must always know that what is momentum operator. Every student should know how to write the expression of momentum operator. But here I am showing you the derivation part, that how you land up with this expression. So, for an electron wave, when electron acts as a wave, what is the wave function? Mathematically, how can you express it? That is psi equals to a into exponential 2 pi I x upon lambda. This expression I have already told when we have done when we are doing the derivation of Schrodinger equation part. At that time also I have discussed about the standing wave or the stationary wave, that electron is acting as if it is like a wave, and at that time this expression was already discussed, that the wave function is given by, that is a mathematical function, is a, which is the into exponential of, in brackets, 2 pi I x upon lambda, and lambda is the wavelength of the wave. Now, everyone knows that differentiation of e to the power of x is e to the power of x, that is exponential part. I have instead of e to the power, I have written exponential exp into brackets, and whatever the constant is always comes out and it is multiplied prior to it. So, a is a constant, it will remain as such. What is the differentiation of exponential? So, it is, the constant is 2 pi I upon lambda. So, 2 pi I upon lambda, it will come out of the brackets. So, this will become a 2 pi I lambda, and exponential part will remain same. So, it is exponential 2 pi I x upon lambda. Because a into exponential 2 pi I x upon lambda is already represented as psi. So, I have used equation number 1 which is shown, the above equation, and I have marked this as equation number 1. This you can see on the slide. I am repeating again that a will remain as such. Whatever I have just simply done the exponential, the differentiation of the exponential part, the constant has come out of the bracket and the exponential part is remain the same. So, I have taken the thing into brackets and used the above equation, I have put it psi into it. Now, using the de Broglie equation, what does de Broglie said? De Broglie calculated the wavelength of the matter waves, that every material particle has got waves attached to it, and the wavelength of the wave was calculated by lambda equals to h upon p. On rearranging that, I have taken the reciprocal, that is 1 by lambda. So, it will become px by h. Now, this again I have marked this as equation number 2. I will put this equation number 2 in equation number 1. You can see our equation number 1 was 2 pi I upon lambda. So, instead of 1 by lambda, I will be using px by h. So, the above expression, that is equation number 1, will become d psi by dx 2 pi I, instead of 1 by lambda, will put px by h. So, this will become, in brackets I have taken px by h into psi. Once this equation is obtained, I will rearrange this. I have taken px and put it caret on it, because in the next step I will calculate it as operator, because we are calculating the momentum operator, that's why I have put it a caret on it, and then psi, and taking all the other things on the right hand side. So, it will become h upon 2 pi I d psi by dx. Because you can see, always in a mathematical operation, mathematical expression, there are always two things. In the quantum mechanics, I am basically talking about the quantum mechanics, because in the quantum mechanics equation, whether it is the most important thing was the Schrodinger equation, we always have an operator which is working upon, which is operating upon a function, and the answer is coming out. So in an equation, in a quantum mechanical equation, we always have two things in it. One is operator, other one is function. So once the function is taken out of the equation, what we are left with? We are only left with the operator. So suppose we have this equation, px operator into psi h upon 2 pi I d psi by dx. If I remove this psi out of it, then what are we left with? We are left with the operator. So because in the quantum mechanical equations, we always have the operator as well as the wave function. The two things are there. So if the wave function is taken out of the equation, we are always left with the operator, and this is what is happening in the above equation. So suppose we have px into psi h upon 2 pi I d psi by dx. If I have taken the psi out of it, then what are we left with? That is px operator. So your px operator would become h upon 2 pi I d by dx. Now I have already told that h upon 2 pi, you can write h upon 2 pi as h cross, and we have also iota with us. So one by one I am showing you the calculation, the simpler form or the different forms which you can see in different books, how they show the maybe in one of the books it is given as h upon 2 pi I d by dx. Maybe it happens in the other book, it is written as h cross. So what is h cross? H upon 2 pi is simply h cross, and I is already there. Now in some books you may find that minus of I h cross. Now what is minus? When iota is taken from denominator to numerator. This you can also see over here, you can see in the expression of p operator which I am writing, that is px operator, that iota is being shifted from the denominator to numerator. Once it is shifted, there is a negative sign, and again if it comes down, the minus sign will vanish. So these three expressions, these are the different kind of expressions which I have put it over here in the slide. Similarly, this because the x component was there, so I have taken px. If the y component is taken, then it would become py. If the z component is taken, it will become pz. So by in this way we have three components of that momentum operator, that in the x direction, in the y direction, or in the z direction. The expression will remain the same. The only thing is that instead of x, we will take y and we will take z. So on the whole, when we add all these three expressions, that is the total momentum operator is px, that is p operator. So p operator is px operator plus py operator plus pz operator. When we add these three, minus I h cross will come out, and in the brackets we are left with d by dx plus d by dy plus d by dz. These are the simple, you can see on the slide, I have simply added the three expressions. Now in the first slide, you can see the first slide, that is where I have shown you the Laplacian operator. What was the Laplacian operator? That is del. What is del? Del is I d by dx, j d by dy, or we can simply write d by dx plus d by dy plus d by dz. And now I am using that Laplacian operator. I am putting that Laplacian operator instead of this. So the bracket, you can put the bracket as del, that is the Laplacian operator. So what is the total momentum operator? It is minus I h cross del. This is the momentum operator, and this you have to keep in mind, that what is the momentum operator. Now we will discuss the square of the momentum operator. Simply we have to do the squaring part. So after the break, we'll discuss more about the operators. Thank you. So we have already discussed about the Laplacian operator, the expression of Laplacian operator and the momentum operator, and now we will discuss the square of the momentum operator. So the square of the momentum operator is the momentum operator which we have discussed in the second point was I h cross upon I d by dx. So we simply have to take the square of it. So suppose we want to calculate px square. You can see the slide, the expression is given on the slide, px square. So px square is h cross upon I d by dx. Again simple multiplication, h cross by I d by dx. Now h cross, simply it becomes h square. Now what is I square? I square is minus 1. It is given that I into I, the iota. It is not that simple I cap. I cap is a different thing. When I cap is multiplied with I cap, it comes out to be 1, but it is iota, it is not I, it is iota. So when iota is multiplied by iota, it will become iota square, it comes out to be minus 1. So the expression would be minus h cross square d square by dx square, and similarly we can calculate py square, which would be minus h cross square d square by dy square and pz square. And when we add the three things, px square plus py square plus pz square, and minus of h cross is taken, h square is taken outside common. So we are left with the bracket d square dx square, d square dy square, t square dz square, and again like in momentum operator we have used the Laplacian operator. We have put it delta into it, but in the square of the Laplacian operator is being used. So the p square, that is the square of the momentum operator, would become minus h square into the Laplacian operator, which is given in the first expression of the operators. This will become del square. Now that is the linear momentum which we are discussing. Now we will discuss about the angular momentum part, that is the expression for the angular momentum operator, that is L operator. Angular momentum is given by the vector product of position operator and the linear momentum, which we write it as P operator. So when the two are cross multiplied, that is by making a matrix out of it, we will get the angular momentum part. So what is position operator? Position is simply the three coordinates, that is x into I cap, y into j cap, z into k cap. And what is momentum operator? It is px into I cap, the py part and the pz part. Now everyone know that how to make that the matrix part, that is I, j and k. We are taking the cross product, we are taking. Now what is r? Instead of r and p, we will put the two expressions and make a matrix out of it, that is I cap, j cap, k cap, and then we will write x, y, z, that is the coordinates of r vector, and then px, py, pz, that is the coordinates of the p operator, that is the p vector. Now once we multiply, everyone must be knowing that how to calculate the cross product. In case one does not know, then you can see on the slide, I have taken the I cap and multiplied the two things which are out of that thing. Again, put your fingers or put your hands on the rows and the columns which is having I. Then we are left with what? P, we are left with y. You can see the slide, we are left with y, z, py and pz. Just cross multiply both the two. So we are left with y into pz minus z into py. This you can only correlate with that matrix part. and then minus j for the calculation of the j part, the j bracket. Just put your hands on the rows and the column which is containing j. So, we are left with x into pz minus z into px. Similarly, we will do that is the k part. It will be given by x into py minus y into px. Now, with the j there is a negative sign. To convert it into plus sign, we will change and will take a minus sign common in the center of the expression. That is, with j the expression would get reversed. It will become z into px minus x into pz. So, now this expression of L, I have marked this expression of L as equation number 3. One should always know that, one must know that there is another expression of L operator, which is in totality the addition of all the 3 components, that is Lx I cap, Ly j cap, Lz k cap, and this I have marked as equation number 4. When these two expressions, that is equation number 3 and 4, are compared, you can calculate the expression for Lx operator, the Ly operator and Lz operator. So, Lx operator, you can see it is y into pz minus z into py. Now, you already know that in the above expressions, in the expression number 3, in the expression number 2nd, in the second part, I have calculated the expressions for the derivation for the pz and py and px, that is the momentum operator. Just pick all those expressions and put it over here. That is, with y, write h cross by I d by dz, and then minus of z, and what is your py? H cross by I d. So, I am simply using the expression of the momentum operator which I have derived in point number 2, and then I am taking h cross by I common. So, in the bracket I have left with y into d by dz minus z into d by dy. So, this is how we will calculate the expression for the angular momentum in the x direction, in the y direction and in the z direction. The same thing is to be done with all the 3. Now, I will discuss the kinetic energy operator. Everyone knows that what is kinetic energy, what is the expression of kinetic energy. So, kinetic energy is written as T. In quantum mechanics, or even though it is written as kinetic energy, the symbol of kinetic energy is capital T. And classically, it is the formula is half of, every student read this expression from, I think from class 7th only they start reading this expression in physics. So, the expression for kinetic energy is T equals to half of mv square, and m is the mass of the particle and v is the velocity of particle. And one more expression, that what is momentum? Momentum is the linear momentum, P equals to m into v. If we take the square of the momentum operator, it will become p square equals to m square into v square. Now, divide this expression of p square throughout with 2m. So, it will become p square by 2m and m square into v square divided by 2m. In the right hand side, m will get cancelled. So, we are left with p square by 2m half of mv square. In the same slide, you can see that is the first expression, we have T equals to half of mv square, and in the last expression you can see that p square by 2m is also half of mv square. So, equating these two, that is the first expression of this slide and the last expression, because both of them are half of mv square. So, on equating the left hand side of both the equations, our T becomes, that equation number 5 and 6, it will become T equals to p square by 2m. Now, what is p square? In the last point only I have discussed the square of the momentum operator, because I am taking the operator expression on both the sides. I am taking T as T operator, I am making P as p square operator. Now, what is p square? What is p square operator? We have minus of h square, h cross square, del square by del x square, minus of h square, del square by del y square, minus of h cross square, del square by del z square. Taking minus h cross square common, again we are left with that Laplacian operator, the square of the Laplacian operator. So, this is the expression of the momentum, the kinetic energy operator, that is T operator equals to minus h cross square upon 2m upon del square. Now, the next, like in classical mechanics, we have the expression for energy, the total energy. You can see what is the total energy of a particle. Total energy is kinetic energy and the potential energy. The only difference is that in quantum mechanics, in classical mechanics, the expression for the energy we use is E, whereas in quantum mechanics we will be using, instead of E, we will use the concept, we will use the expression H, that is capital, the house, that is H operator, and it is known as H operator because in quantum mechanics we always deal with the operator part. So, what is the H operator? We doesn't have any expression to calculate the energy in quantum mechanics, but instead of that we have operators in quantum mechanics. And what is the total energy? In the classical mechanics we use the symbol E for the total energy, whereas in the quantum mechanics we will use the symbol H in the quantum mechanics. So, we simply add the kinetic energy and the potential energy. So, because in classical we use E equals to kinetic energy plus potential energy, whereas in quantum I am using H operator. For kinetic energy it is T operator plus, and potential energy is always designated as capital V. So, I am putting the expression of T operator, that is minus H cross square upon 2m del square, and potential energy is V, because I have taken, I am taking all the 3 coordinates. You can see in the expression of kinetic energy I have taken Laplacian operator. Laplacian operator is x square, y square, z square. So, that is why I have also written in the bracket x, y, z with the potential energy, because I am taking on the whole all the 3 coordinates of the particle. So, suppose most of the time this kind of thing is asked in the exams usually, that write the Hamiltonian. H is known as Hamiltonian in quantum mechanics. In classical mechanics, like E is the total energy. In quantum mechanics it is H. H is the Hamiltonian for the system. So, suppose there is a system which is containing 2 particles, one with mass m1 and another with the mass m2, and the first one having the coordinates x1, y1, z1, and the second particle with the coordinates x2, y2 and z2. So, for every particle we have a Laplacian operator, let it be del 1, delta 1, and for the second part it is delta 2. So, suppose there is a particle which is system where there are 2 particles, one with the mass m1 and another with the mass m2, then the total energy, the total Hamiltonian is kinetic energy plus the potential energy. Now, we will write the expression for the kinetic energy of the first particle, that is minus h cross square upon 2m1 into del 1 square. m1 is the mass of the particle and del 1 is the Laplacian. Similarly, minus h cross square upon 2m2 del square plus the potential energy, that is x1, y1, z1. You can also write it separately, plus v x2, y2, z2. I have taken in the combined form. So, like this you can take, if suppose there are large number of particles, say I number of particles. So, the H operator would be minus h cross square upon 2. Instead of m1 I have taken the summation part, summation, that is 1 upon mi del I square for all the particles plus v xi, yi, zi. So, today I have discussed about the algebra of operators and the kind of operators which we will deal later on in quantum mechanics and the derivation part of it. So, the next time I will discuss about the eigenfunction and many more properties of the operators.
Dear friends, we hope that through today's lecture you were able to understand the concept of operators and their mechanics in quantum chemistry. On that note, we would like to thank Dr. Amita Dua for coming here and delivering this wonderful lecture. And thank you dear friends for watching our lecture. Stay tuned and keep watching. Thank you.